Hi everyone. So today I want to talk about kind of what you saw in those Khan Academy videos. I know sometimes it makes more sense for me than a stranger. So if we're going to set up a voltaic cell, now we talked before we left, and it was a month ago, but we talked before we left about how I can take two halves of a reaction, kind of separate them, and force the electrons to go through something outside. So like I can put a lamp right here. This is my wire. Okay, and it would light up my lamp. And I can use this chemical reaction to make something actually run. So we're talking about how we're going to set this thing up. And we're going to make a copper and magnesium cell. So the first thing I need to know is what's going to be oxidized, what's going to be reduced. Now, usually I've given you a reaction, and today I'm just going to tell you I have copper and I have magnesium, and we have to decide which one's going to do what. So how would we ever possibly know? And the answer looks like that. You remember this thing? You know you do, right? So I've got this reactivity series of metals, and you know from Chem 1 and beginning of this year that a more reactive metal will be able to displace a less reactive metal. So the more reactive one, in this case it's our magnesium here, is going to start off as the neutral metal and end up in the compound, whereas the less reactive element, our copper, is going to start in the compound and end up as a neutral metal. So let's write out that reaction. Now we know what that reaction is. We're going to take, what did I say? Okay. Our neutral magnesium, which is my more reactive, plus copper compound. Now, it can literally be any ion, any anion that we wanted it to be. I can use chloride, I can use nitrate. I'm going to use sulfate because these each have 2 plus charges, and so I'm going to use that 2 minus, so everything cancels and I don't have to keep track of subscripts. So, SO4, okay. Oops, it's a bad arrow. Try it again. Okay. We'll make, and we said they're going to end up with copper plus magnesium sulfate. Okay. So I know what's going to happen, so now I need to find my 2 half reactions. Okay. My magnesium goes from simply being an Mg to this MgSO4, but like we said a minute ago, those anions, those sulfates, are not doing anything in this process at all except hanging around so that we don't have actual charges. They're canceling the charge out on one side. So we don't care about them at all. What I have is magnesium turning into magnesium 2 plus. Now remember my magnesium, this is a solid substance. This is an aqueous substance. So what you're going to see from the magnesium is we're going to start off with solid magnesium and it's going to turn aqueous. Well, aqueous is a water-dissolved solution. So the reality is that you're not going to see these magnesium atoms anymore. You can see solid magnesium, but when it's dissolved in water, like if you're looking at salt water, you don't actually see the salt. When we're looking at magnesium water, you're not going to see these magnesium. You're going to visually, it's going to look like the solid magnesium disappears. On the other hand, I have copper, which had a charge up here in its compound and was aqueous, is going to become solid copper. So again, we can't really see the aqueous substance, but we can see the solid. So we're going to see more and more copper appear while more and more of our magnesium disappears. Okay, now we need to know which is which half of the reaction. So I have a 0 charge goes to a 2 plus charge. This charge got bigger. So since our oxidation number goes up, this is our oxidation half reaction. And then our 2 plus goes down to a 0. The copper has been reduced. Okay, so over here in our cell, what are we going to do? By convention, we always put the oxidation half cell on the left and the reduction half cell on the right. So we're going to put the magnesium over here, which means this strip of metal is going to be magnesium, and this solution in here is going to be magnesium sulfate. Okay. And in here on my reduction side, this strip of metal, we're going to label it as copper, and we're going to label this liquid in here as copper sulfate. Okay, now you'll notice that the magnesium sulfate and the copper are products. They don't actually do anything in this reaction. Not to confuse you, so if I lose you in the next sentence or two, you can ignore them. It's not actually important that this is magnesium sulfate. We could put pretty much any ion solution in here. We could have put salt water in here and it would have been just fine. Same thing goes for the copper. I could use just like any conductor in here. I could have just put a piece of graphite from a piece of pencil lead in here. I could have put an iron nail. It does not make any difference what this is right here. It's the magnesium and the copper sulfate that are really doing the work here. So they're the things that are important. It's not super important what this metal is and what that solution is. Anyway, okay, back to what we're talking about. We've already discussed this is our oxidation half cell and this is our reduction half cell. Well, I want to come back to our reactions for a second. These aren't balanced reactions. My magnesium here turns into magnesium 2+. Now, on the worksheet that we did on Friday, several of you felt the need to put a 2 here. You have one magnesium atom turns into one magnesium ion. We don't need any extra numbers in front of the magnesiums. What we do need are electrons. We need electrons to cancel the charge. So this solid magnesium here becomes magnesium 2+, but there's a positive charge on this side and 0 charge on that side. I need there to be 0 charge over here as well. So we're going to add 2 electrons. Now what this reaction means is I start with this magnesium and it releases this magnesium salt and it lets go of 2 electrons. So these 2 electrons are going to go up and over that wire. They're going to come out of that half cell. Okay. On the other hand, my reduction half cell, and I write it here because I'm kind of running out of space, I have my copper 2+ becomes, oops, let's put some face labels. Okay. Solid copper on this side. Well, now again, I have 0 charge here and I have a 2+ charge here. I need them both to be 0, so I'm going to add 2 electrons to this side. We can see this magnesium spits out 2 electrons and they come all the way over here and go in to that half cell. So they're going to come out of the oxidized half cell and back in to the reduced one. So now we talk about cathode and anode. Okay, the cathode, right? We know that cat ions are positive. Okay, we know that cat means the positive half. Well, let's think about, you guys know enough about charges and how they behave from grade school to kind of be able to logic your way through this. A positive thing is going to attract to negative things. So it's this side over here that's attracting the electrons to it. So that makes this copper half cell my cathode. Okay, you can look at, oh, never mind. That's good enough. The positive side should attract the electrons. The electrons should get pulled into the cathode side. The anode, right, we know the An equals is a negative charge, so my negative side should be repelling electrons, should be pushing them away. You can also look at it as the negative side has an overflow of electrons. The electrons are spilling out of this negative thing. Okay, there's so much negative on that anode that it just like spits them out. Okay, so that's my magnesium half cell over here. This is my anode. So again, I asked in the doc what it looks like. What are you really going to see? Well, the oxidation half cell is going to look like a piece of magnesium and some magnesium sulfate. The reduction one is going to look like a copper in the copper sulfate. The anode is always going to be the oxidation half cell. Remember, oxidation is a gain in charge. So the charge is always going to get more positive over here. In order for something to get more positive, you have to lose electrons. Same thing for the reduction. The reduction is always going to attract more electrons. It wants more. It's going to suck more electrons into itself. Okay, is going to make that side the positive cathode. What was the other question I asked? Oh, what's it going to look like? And we looked at that a couple times already. This on the anode, on the oxidation side, you're always going to see solid metal turn into a solution. You guys have heard the word oxidation before, referring to things like rust and like the crud on copper pennies. Well, it's when you take a solid metal, nice metal that is usually what we want, and we kind of make it all cruddy, turn it into a salt, an ionic compound that usually isn't what we want. When a metal oxidizes, it goes from copper to that copper garbage that you see all over your pennies. So the oxidation will be a solid turning into, in our case, it's going to be a solution because it's in water. Our reduction will be taking those ions, taking this solution right here and turning it into actual solid copper. So on the reduction half cell, you're going to see metal, more metal showing up on this strip right here. Okay, hope that helps.